All right, guys, so let's get into our introduction of quadratic expressions and then also introduce what factoring is all about. So let's take it back to something much more familiar, hopefully, and generally in algebra classes as you're coming up. The first type of functions that you work on are linear functions, where of course they just look like y equals mx plus b. So there's no exponents on the x. And solving an equation is relatively simple because all you have to do, for example, I don't know, let's just say it's like 3x plus 5 equals 9 or something, right? And if you're going to solve an equation, all we got to do is use inverse operations. Subtract 5 from both sides. 3x would equal 4. And then you can just divide both sides by 3. Oops, so x would be 4 over 3. Okay, so we can kind of solve that with just addition, subtraction, multiplication, and what else did I miss? Add, subtract, multiplication, and division. Okay, whereas quadratics now, the main difference in their equation, okay, there's a couple ways to write the equation, but it's going to have x squared in there, plus bx plus c. So it can have an x squared term, and then it can also have an x term as well, okay, like this one that linears have. So the new addition obviously is having this x squared term. And we're going to get all into their graphs and how to deal with them and everything real quick, preview or whatever. They're going to look more like a U like this. It's called a parabola, okay, where of course linear functions are just lines, okay. So things get a little more complicated, a little more going on. When you go to solve something like, let me just make one up, 3x squared plus 4x plus 2 equals 8. Okay, issues start to arise because you might just be thinking, all right, can't I go ahead and just get the x by itself, right? So, well, maybe we could subtract 2 and get 3x squared plus 4x equals 6. And then the problem is there's more than one x, right? You have the 4x here, but then you also have a 3x squared. So you really can't get them like both by themselves, right? So there's other methods that need to be involved here. And factoring is one of the big ones in order to solve equations, and it'll help us with some other things later when we try to simplify other expressions. Okay? All right, so before we actually get into factoring things, let's look at multiplication. Okay, so kind of a review. If we wanted to multiply these three things out, of course we're going to call it distributing. So we would multiply the x by each of those. Right? So we would end up with 3x squared minus 4x for the first one. Okay. Part B, this is one we commonly call the FOIL method because you're basically just distributing. Take the x times x, so that's multiplying the first terms. Then the x times the plus 6, those are the outside terms, so the O in FOIL. And then we move to the 5 times x, which is the I, the inside for FOIL, right? So that's plus 5x. And then 5 times 6 is the last, if you're using that FOIL little acronym there. So really foiling is just distributing, right? Just makes sure that you don't miss any terms. And then we can combine the two middle terms many times here, and we would get x squared plus 11x plus 30. Okay, and then with part C, same kind of problem. It's multiplying two, these are called binomials because they each have two terms. So x times x, again, is x squared. X times the plus 2 is plus 2x. The minus 2 times x, and then minus 4. Okay, and this one's going to simplify x squared. With the plus 2x and the minus 2x cancel out. So this one just ends up equaling x squared minus 4. Okay, so that's just multiplication, right? That's something we should be, kind of familiar with, done quite a bit of that. The issue, or the new thing I should say, is this idea of factoring is where you would take, for example, this answer and be able to figure out what the multiplication problem was that got it. Okay, you're kind of unmultiplying. So it's kind of like dividing in a way, but it's definitely not exactly the same as dividing. But you are definitely unmultiplying things. So for instance, if I give you a problem like x squared plus 11x plus 30, we need to come up with a method to figure out that equaled x plus 5 times x plus 6, kind of working backwards, okay? And there's some tricks and there's some methods in order to do that, and we'll get into later about what it actually does for us. But it is pretty big. It comes up in quite a few sections and a lot of math questions, so make sure we're on board with this topic and don't fall behind on it. Okay, so I want to look at, focus in on part B. Okay, I know there's a lot of writing on the page here, but on part B, if you take a look, our answer was x squared plus 11x plus 30. Okay, take a look at the answer, or the factors ended up being x plus 5 and x plus 6. Okay, do we see where the 30 came from? Okay, the 30, when we did our FOIL, was the last thing. That was just the 5 times the 6, right? Okay, so I know that 30 was the 5 times 6. And take a look at where the 11x came from. Okay, do we see these middle two terms here added up? They combined to the 11x. So that was really the 5x plus the 6x. Okay, so keep that in mind, and let's go back and see if we can get our problem going. In part C down here, remember how these middle terms right here canceled out because it was an x minus 2 and an x plus 2? And look at the answer. It ended up being just two terms. Okay, it was the difference of perfect squares, x squared minus 4. Okay, so let's go back, before we talk about doing more complicated ones, let's go even back to pre-algebra days, maybe back even in middle school or even elementary school when you were thinking about prime factorization. So let's say I wanted the prime factorization of the number 50. Okay, so we want to think about, remember making factor trees? Right, I want to think about, all right, what times what equals 50? Okay, so there's a few ways to do it, right? We could say, well, 10 times 5 equals 50. But that 10 is still factorable into 2 times 5. Okay, so now everything we have at the bottom there, each of those are prime numbers, right? They have no other factors except themselves and 1. So the prime factorization could be thought of as 2 times 5 times 5. Okay, so that's 50. That's prime factorization. What if someone else is saying, well, I did 50 a different way. I thought of 50 as 2 times 25. Right, and then when you keep going though, 25 again is 5 times 5. Now everything's prime. Now we can recognize it's the same prime factorization. So it doesn't really matter what path you take, okay? As long as you factor until things are prime, then you're going to get the same prime factorization. So I just wanted to show that example. That's another example of what factoring is. It's kind of in a way of like unmultiplying. Okay, and again, it uses division like kind of behind the scenes, right? I mean, we weren't really thinking division, but division's definitely related to multiplication. But what we did when we got these are going to be the factors, and in this example, we did it all the way, so those are the prime factors of 50. Okay, and there's no other prime factorization of 50, right? 2 times 5 times 5. So that's factored. A little method to. All right, so let's look at some more algebraic expressions, because of course this is algebra class, and we want to deal with variables and make things more exciting and more fun. Okay, so what we want to do, one thing I always want to remind you guys of, no matter how far you get into this stuff and you're factoring in calculus and then still showing up and whatnot, always think, can you find the greatest common factor first? And just look for that and do that first. Okay, so what I mean by that is think about in these two terms here, we have a 12x and we have a 36. If there's any factor that goes into both of them, it's going to make this problem so much easier if we factor it out first. And sometimes that's the only thing you can do. So like in this case, the only thing we could do is what's called factor out this greatest common factor. So some of you guys might be thinking, well, 3 goes into both of them. It's true, but so does 6, and so does 12 even. Okay, and what we want to do is make sure we get the greatest common factor because it will cut down on the number of steps we have to take. So what we're going to do, we're going to kind of factor out a 12. Okay, and imagine now we're going to ask ourselves, what would we have to multiply 12 by? Okay, we're kind of like doing the distributive property backwards. Okay, so 12 times, let me just write it out here. If that's an x, and that's a plus 3, do we see how that 12 times x would be the 12x, and 12 times the 3 would give us the plus 36? Okay, so in a way, once you get the common factor of 12 out, then you kind of are dividing, right? You're dividing 12x by 12. That's where the x came from. And then we're dividing 36 by 12 because the 12 was what's called factored out. Okay, so the final answer to this is 12 times x plus 3. That is the prime factorization. Just like we did with 50, we have now done it with an algebraic expression. Okay, and the reason I know it's done is because each term, or the term in parentheses, I should say, has no other factors. Like x plus 3, there's nothing we can do with it. Okay, what about part B? X squared times 15 minus x. Well, looking at that term and that term, I know they both share at least in common a factor of x. That's going to be the GCF. And in order to get x squared back, I would need to multiply by x. And in order to get the 15x, I would need to multiply by minus 15. Okay, so there's our factored version. Again, check it by distributing. And you can even check in your head, kind of distribute. X times x is going to get you the x squared. X times minus 15 gets you the minus 15x. And that thing, again, is factored. There's definitely a slide when we just... Okay, now for these. This is a very common type of problem. It just seems to show up all over in different sections and different classes even. These are called quadratic trinomials. Okay, and if you remember, we talked about quadratics have the x squared term in there that you can see these do. And then trinomial, of course, tri means 3, so these are 3 terms. And this is just a very common type of problem. So let me go back for a second to the warm-up we did when we multiplied, and then we'll see how to handle these. Okay, so let's go through a little process here. We have a 10 sitting here, right? So what I need, and what a lot of times people will do is they'll make a little list here. We need 2 numbers that are going to multiply to be 10, okay, but they need to add up to be 7. Okay, so with 10, there's not too many options, either 1 times 10 or 2 times 5, right? Okay, so 2 times 5 is the one that's going to add up to 7. Okay, so what we're going to do to factor this, think about kind of doing that FOIL method in reverse. Okay, another thing we're thinking about here, our first term is x squared, so that means the first terms in the binomial factors are going to be x's, right? Because the x times x would get you the x squared. And then we just talked about how the numbers here and here need to multiply to be 10 and add up to 7. So that's why it's going to be a plus 2 and a plus 5. Okay, and that's going to be the answer. Let's just check it because this is our first one. We can always check factoring problems by multiplying them back out. Right, so if I do x plus 2 times x plus 5, it's going to become x squared first, then plus 5x, then plus 2x, then the plus 10, right? That's just doing that FOIL problem like we did a couple minutes ago. And make sure you're seeing now the 10 right here is because the 2 times 5 equaled 10. And the 7x in the problem right here came from the terms adding up to 7. Okay, so let's try another one from the beginning. We have x squared minus 12x plus 20. Okay, so it's going to be 2 factors again, starting with x and x. That's how we're going to get the x squared out of it. Now I need factors of positive 20. Okay, they need to add up to this middle term of negative 12. Okay, so sometimes you got to mess around. There's some options. We need to add up to be negative 12 because that's what I'm seeing right here. So negative 12, but multiply to be 20. How about negative 10 and negative 2? Right, negative 10 times negative 2 is going to get you the positive 20. And the negative 10x minus 2x is going to give you the negative 12x. Okay, so you do need to watch for negatives, and sometimes it's one of each and all that good stuff. So let's do one more. X squared plus 2x minus 8. All right, so what are some factors of negative 8 that add up to positive 2? Okay, so to get 8, I know it's going to be, it could be 4 and 2. Is there a way to make it multiply to be negative 8? One of the numbers needs to be negative, right? So we need it to be a positive 4 and a negative 2 so that they add up to be positive 2x. Okay, so I'm going to make it with a plus 4 here and a minus 2. Okay, now the order you write them in doesn't matter. You could have the x minus 2 first, and then the x plus 4 needs to come in there. Okay, so it doesn't really matter which order you write them in, and that's true for all of these. You know, just like saying 10, you could write it as 2 times 5 or as 5 times 2. Okay, the order does not matter. And the one did. All right, and lastly for this part of the section, these now are just a special case of what we did before. Okay, so the x squared minus 16, it's not a trinomial, but it's still a quadratic, and you could think of it as a trinomial if we inserted in the middle a plus 0x. Okay, then we could use the exact same pattern that we did before. Okay, I would still be looking for factors of negative 16, but this time they need to add up to 0. Okay, so this only works in special cases if it is the difference of perfect squares. And the reason for that is, right, 16 is a perfect square, so I could think of it as 4 times 4, but to get negative 16, it means one of them needs to be negative. Okay, you could also do 2 times 8, right? But the problem is they need to add up to 0, so that's why it needs to be an x plus 4 and an x minus 4 to make the middle terms cancel out. Okay, we saw that back to was x squared minus 16. Okay, let's do part C, and then we'll talk about part B for a second. Part C, x squared plus 25. Okay, so are there any factors of 25 that add up to 0? Because remember, again, there could be a 0x in the middle. So any factors of positive 25 that add up to 0? So it would need to be like 5 and negative 5 to add up to 0, right? But 5 and negative 5 are not going to give us a positive 25. So this rule only applies when it is the difference, okay, meaning subtraction of perfect squares. This thing is not factorable. Okay, it is actually prime. Okay, it cannot be factored with real numbers. When we get into imaginary and complex numbers down the road, it may be able to be done, but at this point, it's not factorable. Okay, so there's nothing we can do. It's like a prime number, you know, like the number 7. Can't factor it. Just 7 times 1, that's it. All right, so in part B, this is more just like a formula, right? If it's anything squared minus something squared, it will always factor into a plus b times a minus b. If you take a look at part A here, that's what happened, right? It was x squared minus 16. So it just became x plus 4 times x minus 4, right? And that's all this is saying here. It's the a plus the b times the a minus the b. Okay, so that's a special case just to watch for. It may be helpful to put that 0 x as the middle term and then just follow the pattern. But it does show up in some problems, and it's just a good thing to be aware of. All right.